received her PhD degree in analytical chemistry from Peking University in 2011 with expertise in PCR technology. Prior to joining the Dana-Farber Cancer Institute in 2014, she was an assistant professor at National Center for Nanoscience and Technology in China, where she established dynamic drug delivery systems for effective cancer treatment. Her current work centers in designing and developing sensitive and specific platforms for molecular diagnostics and therapy, and utilizing novel mutation enrichment and methods prior to endpoint detection. Her work has been published on peer-reviewed journals include NCR, AC, GA, Chemical Societies, More Chemical Communications, and etc. So let's welcome Chen Song to give us the talk today in the Precision Medicine Seminar.
Thank you for the introduction. Thank you for CSSA inviting me to here to the talk. Today I'm going to talk about the recent developments in our lab focused on the mutation enrichment technologies. Actually, in our lab, it's different from many of the labs here because we basically focus on translational projects. So my talks today mainly focused on technology details instead of basic science and biology. So today I'm going to introduce recent developed technology called NamePro. Do we have a And I will explain later what is NamePro. And I will introduce you how did we develop this assay and how we combine it to the current NGS workflow to improve the detection of NGS. And basically our projects in the lab mainly focused on improve the liquid biopsy, which means improve the cancer-related mutation detection throughout the technology we developed. And as many of you know, cfDNA in cancer sample has very low quantity and low quality, and the mutation abundance is very low, usually less than 1% or even 0.1%. Which increase the challenging of detect the informative cancer-related biomarkers. And this study shows the importance of detecting mutations in ctDNA. The researchers detect the single base mutations and the rearrangements, which are the most common variants in the ctDNA. And they found that ctDNA is detectable in most of the cancer types. And in the meantime, within each cancer type, the quantity of ctDNA varies among patients, which requires a very sensitive and accurate method to detect the variants in ctDNA. And also, the ctDNA has a very promising application in the monitoring of response to the treatment. In this study, the researchers detect the KRAS mutation in the blood samples of patients treated with cetuximab. And also, after the treatment, they collect the blood samples at every time point. And also they did radiological assessment at each time point to compare the CT scan and the mutation detection results. And here it shows shows after the treatment, for some time, the KRAS mutation is like about 0 or baseline, but it increased after like maybe 8 months after the treatment, and it reaches kind of threshold, which is 0.1%, which means it is possible to give another treatment like the MEK inhibitor for this patient. But in the meantime, the CT scan shows this effect 10 months later than the KRAS mutation detection. And like I said, the ctDNA is very important right now for cancer diagnostic and also the treatment response to the treatment monitoring. And but the detection method requires high sensitivity and accuracy. Therefore, it's very challenging. There are two main techniques currently focused on the variant detection in ctDNA. One is PCR-based technologies. As you can see, there are several kinds of methods, well-developed methods right now, and it has sensitivity from 0.001% to 1%, depending on the platform. But the downside of the PCR-based technologies is that it is like single target based. If you want to do multiplex, the design effort takes a lot of time, like the digital PCR or beaming method. And another category of the technique is NGS-based technologies. And as you can see here, the whole genome sequencing or whole exome sequencing is well known, but actually the NGS platform can only detect mutation down to 1% because of the intrinsic error of the NGS platform. And the people also developed NGS technologies, followed the PCR targeted enrichment followed by NGS, which in theory can reach 0.0001%. But again, although they reported this detection limit, it is hard to apply to ctDNA currently. And in our lab, we are trying to improve the current detection method by mutation enrichment. So here I'm going to introduce the NAMEPro technology, nuclease-assisted mutation enrichment using probe overlap. So the basic concept of NAMEPro is the starting DNA material will go through the NAMEPro method, and after that, we selectively digest the wild-type molecules, so that in the end, the proportion of mutant molecules will increase. It can increase the sensitivity of all downstream detection methods. And in NAME technology, we basically utilize this specific enzyme, duplex specific nuclease, and we take advantage of the two functions of it. First, it is thermostable. The optimal working temperature is 65 degrees Celsius, which allows us to play with the working temperature. And then it has a strong cleavage preference for double-strand DNA over single-strand DNA. I will show you how we utilize this function. So the design part of NAMEPro is like this. We design a pair of DNA probes which has an overlap part, and those probes bind to the top and the bottom strand of the double-strand DNA with wild-type DNA template, and it will form a mismatch with the mutant DNA. And when we apply the enzyme DSN on it, Because it has a strong preference to cut the double-strand DNA over single-strand DNA, so it will selectively cut the wild-type DNA and the probe duplex, and the mutant DNA will survive. And we use this overlap part as our target region to enrich the mutations. And the workflow of NamePro is like this. We started from the fragmented genomic DNA or circuiting DNA. Like I said, our main goal is to improve liquid biopsy. So usually we do fragmentation of the genomic DNA as a model when we have no access to the circuiting DNA. And the starting material contains both wild-type DNA and the mutant moleculars. And we do denaturation, they became single-stranded. And then we reduce the temperature at 67 degrees, which is optimized for our probe design. At this temperature, the wild-type templates will form a stable duplex with the probes. And the mutant moleculars will essentially keep single-stranded. So when we add the DSN, it will cut the duplex DNA. And followed by PCR amplification, the mutant moleculars will be enriched. And first, we proved our assay with a single target KRAS mutation. So we started with the DNA materials containing KRAS mutation and applied NamePro for it, followed with PCR. And we use digital PCR before and after name to compare our enrichment. We performed several control with it, and as you can see, when both the enzyme DSA and the two probes are present in the mixtures, we can achieve from 0.5% to 80% enrichment, which is significantly enriched. And then after that, we proved the duplex NamePro assay working well with the TP53 and the KRAS mutations. Both of them got significant enrichment. And then we move on to run a templex NamePro assay. And you can see when we started from 5% original mutation abundance, all of them can reach above 60 and even 90%. And the purpose of doing mutation enrichment is to improve the downstream detection method. I showed you before digital PCR platform, which is already a sensitive detection method. And right now I'm going to show you how does it improve the sensitivity of other platforms like high resolution melting, which is based on the multi-profile difference between the wild type and the mutant. So whenever the software shows the profile is different from the wild type profile, it will show you a color and a high peak. So here you can see if without no DSM means without our NamePro assay treatment, it is green means similar to the wild type, and it's considered as negative mutation detection result. And after NamePro, it shows a very high peak, which means the mutation is enriched and can be clearly detect high resolution melting. And the same thing with Sanger sequencing. Sanger sequencing has a detection limit around 20%. So starting from a 5% original mutation abundance, none of them can be detected without our enrichment by NamePro. And after applying NamePro, all of them are enriched and can be clearly detected on Sanger sequencing. And then we are not satisfied actually with 5% because in liquid biopsy, it is really low, like I said, below 1% or 0.1%. So we go further with our technology. Right now we go to 1% for 10 plex, and it shows very good enrichment as the 5%. And then we also extend our panel to 50 plex, and for all the mutations that we tracked, they all have very good enrichment. And then we did a serial dilution study to see how low we can go. So we did from 1% to 0.01%, and all of the mutations can be enriched, but the detection limit is 0.01 to 0.1 depending on the mutation type. And also we did semi-quantitative like correlation graph, because like I showed you, in the DNA material, we selectively digest the wild-type molecules, which sounds scary to some of the people, because you digest the wild-type, but how do you know the original mutation abundance, although you detect it after the technology? So we want to answer the question, can we derive the original mutation abundance from the enrichment data we got? So we did a very preliminary semi-quantitative correlation to prove that if we detect a mutation abundance after enrichment, we may somehow calculate the original mutation abundance, which is important for the molecular diagnostic. And then after the first assay development, we applied the assay to the clinical samples. Like here in the colorectal tumor DNA sample, we enriched the mutations in TP53, and we found the mutation in exon 8 and 9 were enriched, like they were originally not detectable on Sanger, and then they were enriched to 74% and 61%. And the same thing happened with this long tumor genomic DNA. They were all enriched, can be detected on Sanger sequencing. And then we applied name assay to the circulating DNA, which is our main goal. So first, because it is not very easy to find a good sample with multiple mutations in a real patient sample. So we actually spiked with our mutated genomic DNA into a cfDNA background, and we proved that the multiplex name assay still work with the cfDNA sample. And then we applied the assay to cfDNA from colorectal cancer patients, and we found 2 KRAS mutations that were enriched. And then previously I showed you all the data on digital PCR, high resolution melting, and the Sanger sequencing. And none of them can be applied to high throughput analysis. And so then we move on to apply NamePro into the current NGS workflow. So we compare the standard targeted resequencing workflow with our workflow, which we incorporated NamePro at the beginning and follow the same workflow as the standard. And here we got the result showing if without NamePro, the standard workflow cannot detect mutations like 0.2 or even the 2% is like similar to the noise level. And after applying NamePro, we are able to enrich the KRAS mutations to 41, 25, and 6%. And most importantly, the noise level keeps the same as before. And also the same thing happened with IDH1 mutation, like from 0.8 to 13%. And also another two targets, BRAF and the MERK2. And for this initial attempt on develop NGS workflow, we are not very satisfied with our data, although we got the positive enrichment, because the major challenge with NamePro assay is that it digests most of the wild-type moleculars, which means although the mutant-type moleculars survive, the DNA input is much lower than the original DNA material. So when we apply this digested sample into the following PCR reaction, they will generate non-specific amplification because of the low DNA input. So which means in the NGS detection, we lost many of our on-target reads. So which means one is a waste of the reads, and second, we didn't get the reads we supposed to have, so which limit our ability of detect a really low mutation abundance, and also some of the DNA applicant targets were lost during this process. So then we optimize our NGS workflow, and it worked essentially well. And then so we move on to apply the new NGS workflow to a new project, which we call the tumor fingerprint in ctDNA. So in this project, it's essentially we are able to get cancer patient ctDNA samples, which were screened by whole exome sequencing, and also our collaborators did whole exome sequencing on the tumor DNA of the same patient. So basically, we have the data of mutations in tumor DNA and the ctDNA. And when we compare them, there are overlaps in both DNA samples. But some of the mutations only occur in tumor DNA or only occur in ctDNA. And there are many reasons why they don't have overlap. I don't have time to go to the details. But right now, in our project, we just want to ask a simple technical question. So how can we increase the number of detectable tumor biomarkers in ctDNA by simply improving the NGS sensitivity? And our mutation enrichment method can do this. So basically, we use our customized workflow and the NGS panel. We applied NamePro and follow this workflow. And the result shows for the first patient we tried, we chose 50 targets to do a multiplex name, and then the NGS workflow. And as you can see, for the 50-plex, which were not detectable on the whole exome sequencing detection, but like 31 targets were enriched and detected in our workflow. And this part shows the lower ones. And we also ask another question: how do we trust our detection, like our claim of the detection? And we also analyze the noise level of half of the targets, which has essentially has lower enriched mutation abundance, and we plot the variant frequency and the maximum maximum noise frequency. As you can see, most of them has a much higher variant frequency than the noise frequency. And here we are able to claim our detection limit is 0.1% because here essentially after enrichment the detection is about 1%, but considering our enrichment is most of the time is higher than tenfold. So right now we claim the detection limit is about 0.1% of original variant frequency. And this is just a simple DNA NGS workflow without molecular barcodes or advanced algorithm. So if we can do those advanced tools, we probably can get even lower detection limit. And by looking at the current detection platform, usually people started from genomic DNA and the ctDNA, followed with the PCR, all kinds of PCR and the downstream detection method. And I hope I convinced you today that by incorporating NamePro into this workflow, all of the mutation detection methods can be increased. The sensitivity of those methods can all be increased by applying this new workflow. And most importantly, if we take advantage of the massive parallel ability of NamePro, it is very compatible with current NGS sequencing technologies and improve the molecular diagnostics based on that. And I would like to thank all my colleagues in Mike McRitch August Lab and our collaborators in Dana-Farber and Broad Institute and NUD. And thank you.
So for the enzyme used in NamePro, what kind of enzyme do you use? Is that general?
It's a commercial product.